Okay, so let me remind you where we were. At the end, I want to work with an algebra QU. Doesn't matter, I may not reach there, but I will reach as far as I can. And this algebra, in this algebra, basically everything works. But it's still too hard, and it's hard to motivate it, and it's hard to explain several things about it. So I want to work with the classical version of the quantum U, which is CU. I wrote CU on the board before, and it's on the handout, so I don't need to repeat it. And even less so, I need to repeat this. But I do need to repeat this because I want to talk about it. Sorry, so maybe I'm contradicting myself. So we mentioned that the generating function of the multiplication in CU, so I call it CMIJK, is the exponential of something called lambda. And the main thing I want to do today is to finish the proof that this is right. So I still owe you the completion of the proof. So basically, we have half the proof and we need the second half. But still, lambda is given by this ugly formula written here, which previously I told you that I've never typeset or written it myself, and it is now a lie, because for the first time ever I have written it myself with my own handwriting. But before struggling to prove this theorem, the fact that this is lambda, what's so good about it? It looks ugly. It doesn't look good at all. Okay? So I expanded it as a power series in epsilon, and that's still in the handout, and I copied it nevertheless. And if the copying is wrong, it's completely irrelevant. The thing in the handout is absolutely correct because it was generated by machine. Okay? Anyway, when I expand it as a power series in epsilon, I get something which is independent of epsilon plus a term proportional to epsilon plus a term proportional to epsilon squared plus higher order terms. I remind you that our technology for composing such things, so for composing the exponentials of such things, works if it is a perturbed Gaussian. So if the first part is quadratic, and then a docile perturbed Gaussian. So if the first part is quadratic, and the part proportional to epsilon is a polynomial of degree at most 4, so 2 times k plus 1 plus 2, where k is 1 because it's epsilon to the 1. And the part proportional to epsilon squared is a polynomial of degree at most 6, basically if it's a docile power series. And unfortunately, this isn't the case here. Because if you look carefully, I mean, this looks quadratic enough, and this looks quadratic, except it has a coefficient e to the minus alpha. What's the exponential doing here? You can't have an exponential in a quadratic. Likewise here, this isn't docile because it's not a polynomial. I mean, if you count the number of variables that appear here, it may look good, but then comes these exponentials which ruin everything. Okay? So I want to tell you what's good about this expression. Even before proving that it's right. Okay? So what's good about it is that it's a docile perturbed Gaussian in the second sense, or let's call it DPG2, and just like docile perturbed Gaussians were a category, you can make a category out of out of docile perturbed Gaussian in the second sense, in the sense of 2, and everything about CU and QU, and in particular CM, is inside that new category. So I have to explain what is an exponential or an element, a generating function in DPG2. So for DPG, for docile perturbed Gaussians, I wanted omega e to the q plus p, where omega was a scalar, q was so a quadratic with scalar coefficients, and p was a perturbed, was a docile perturbation. Okay? So in DPG2, it's the same, except a few things change. So first of all, the quadratic is decomposed into the sum of two quadratics. So L and Q are both quadratic. So L, but they're different, I'll mention in a moment. And P is still a perturbed Gaussian, and a perturbation, a docile perturbation. So let me define each of the terms here. But before defining them, I have to tell you that the variables are not treated equally. Like before, the variables were treated democratically. Basically, the x and the y's and the pi's and the x and the p's and the pi's and the xi's were all the same. But here, the variables have slightly different roles. And the way you summarize the roles is by saying that each variable has a weight, and the weights are slightly different, and different weights are treated differently. So the weights of the variables y, b, a, and x, and their duals, eta, beta, alpha, and psi, are defined to be, this is 8 definitions written in one line. Okay, the weight of y is 1. The weight of b is 0. The weight of a is 2. The weight of x is 1. The weight of eta is 1, 2, 0, 1. Okay? Notice that the sum of the weights of a variable and its dual is always 2. So notice that the weight of any zeta plus the weight of any of its dual, zeta, not psi, is always equal to 2. Okay? And I also have to redefine what a scalar means. So, the thing is that I now have two types of scalars. So I will call them scalars. So a scalar is anything of weight 0. So a power series in the weight 0 variables, meaning b and alpha. And there is the real scalars, the scalar scalars, which are just the rational numbers. So I will simply call them rationals. So, you know, rationals are even more scalar. I'll just call them rationals, okay? So here are the conditions on generating functions in DPG2. So omega, the prefactor, is a scalar. So a scalar now means a power series in the weight 0 variables. In the case of Cm, it is 1, but it doesn't stay 1. Okay? L is a weight 2 quadratic in, so, you know, I'll remove the rationals because it's really not saying anything. So L is a weight 2 quadratic in the weight 0 and 2 variables over the rationals. So it's a quadratic in the weight 0 and 2 variables, but the coefficients are rational numbers. Q is again a weight 2 quadratic, but now in the weight 1 variables, but not over the rationals, but over the scalars. So the coefficients of Q can be can be power series in alpha and B. And finally, P is a docile perturbation. So P is the sum as k is greater than or equal to 1 of epsilon to the k pk, where the condition on pk is that the weight of every monomial in pk is less than 2k plus 2, the same 2k plus 2 as before, except now it's with weights, not with degrees. Basically, degree is just weight if all the weights are 1. So basically, the old case is the case where all the weights are 1. Okay? Now, the coefficients here, I didn't say what the coefficients are, because I don't need to. Because the weight of degree, because scalars have weight 0. So the coefficients are, well, basically I want the total weight to be less than 2k plus 2, and this allows arbitrary weight 0 coefficients. But you know, just to be complete, I will say with scalar coefficients, even though it's already implied. Okay? So, first thing to notice is that the expression written here is of that form. Okay? So, omega, as I mentioned, is 1 in this case. So I just have e to the lambda, and uppercase lambda indeed decomposes as a sum of L plus Q plus P. So, this is an L part. This is weight 0 against weight 2, so it's a weight 2 quadratic. This is weight 1, weight 1, weight 1, so it's a weight 2 quadratic. Sorry, so this is a weight 2 quadratic in L. Maybe I should mark where the things belong. So this is an element of L. This is not an element, a part of L. This is degree 1, sorry, weight 1, weight 1. So with coefficient, which is a power series in weight 0. So this is a part of Q. This is weight 0, and the betas are weight 2. So this is weight 2. Sorry. So this, this decomposes into two parts. The part with the betas is in Q, and this part is weight 1, weight 1, and you can think of this beta as a coefficient, this B as a coefficient, and it's weight 0. So this is a part of L. This whole thing, I believe, is a part of Q. Okay? And now if you look at the perturbation, all I have to check is that the weight of every coefficient of epsilon is less than 4, and the weight of every coefficient of epsilon squared is less than 6. And you can just count. I mean, this is 2 plus 2 plus 0, so this is the weight 4. This is 1 plus 1 plus 2, because A is of weight 2. So this is again weight 4. I won't go through everything, but the point is that all the exponentials don't harm anything, because they're always exponentials of weight 0 variables. And you can check that here everything is weight 6, and it's very, very easy to check by direct computations that if you continue these expansions, it remains docile. Okay, so now we know what is DPG2, but can we work with DPG2? Right? I mean, we worked hard to know how to compose such things, and can we still compose? Okay, so the answer is more or less. So we need to understand how to contract an F against an element of this form. What should I call this element? I want a common name for, so an F against an element, just a writing, element of DPG2, where F, so the way we do the contractions is, it's a quadratic, but it's a quadratic in which you always pair a variable with its dual. So this is a weight 2 quadratic. Okay? So I'll do it in two parts. So first, if you have a weight 2 quadratic, it decomposes into the sum of two things. One thing of weight, a weight 2 quadratic, and in fact, with coefficients, in fact, all of the coefficients are 1 when you start. Right, because this is really, this was born in the form e to the sum zeta I zi. So, okay? So with coefficients in Q. Okay? Weight 2 quadratics with coefficients in Q decompose into a sum of two things. The part where you have, F becomes a sum of two parts, F02 plus F11. So this is where you pair a weight 0 variable with a weight 2 variable, and this is the part where you pair a weight 1 variable with weight 1 variables. Okay? So I'll do these contractions in two parts. So basically, this is equal to, well, you could contract the weight 1 variables against the contraction of the weight 0,2 variables against that same element. Okay, so basically, you first do all the differentiations in the 0, 2 variables, and then all the differentiations in the 1, 1 variables. You can do that. Okay? So basically you do it in 2 steps. And by the way, the 2 steps commute. I could do it in the other order just as well. So I just need to look at elements of DPG2 from 2 perspectives. Okay? I need to look at them first from the perspective of 1, 1, and then from the perspective of 0, 2. So E from the 1, 1 perspective, in other words, suppose I want to glue, to zip the 1, 1 variables, to contract the the variables of degree 1, then let me rewrite E in the following form. I write it as omega times e to the L times e to the q plus p. Okay? And I think that my ring of scalars, so you see, everything I did before could have been done over an arbitrary ring. So now my ring of scalars will be power series in weight 0 variables. So, so this is done over what I call the scalars, namely power series in weight 0 variables. And then, well, omega was a scalar, and e to the L, oh, no, e to the L is not quite a scalar, I forgot. It has, weight 2 things in it. But it's irrelevant, they're constants, they don't participate in the gluing. So, you know, maybe so I shouldn't have called this a scalar, I should have called this a constant. This is a constant from the perspective of the 1, 1 variables, of the variables that I glue, that I differentiate. So it's irrelevant, it just doesn't participate, it's a prefactor. And then Q and P, so Q is a quadratic with coefficient scalars, and P is a perturbed Gaussian with coefficient scalars. So we know how to contract this. So this is doable. In fact, the exact same programs we have will work on this. We just have to specify that the variables we glue are the y and x and eta and psi, and ignore the other variables. So they work literally exactly the same. Okay? And now the same thing from the 0, 2 perspective. So now I want to write it as e to the L plus q plus log w omega plus p. And think of it as no, sorry, I did it wrong. Exactly how do I want to write it? Well, I'll keep it this way, but discuss it in a moment. So here, this is the quadratic, so this is the quadratic, and it's of course over Q. And I think of all of these as perturbation and it is still docile. It is still docile because, I mean, even though this part has epsilon to the power 0 in it, you just extend the definition of docile to include epsilon to the power 0, and then the weight should be so the weight of P0 should be less than 2, and the weights here are less than 2 because this is quadratic and this is weight 0. Okay? Now, okay, but it's not quite as easy as this part because there is still a complexity. So, or an issue. So basically, so you do, I mean, okay, the issue is that the perturbation maybe is maybe docile from the perspective of weight, but not from the perspective of degree in the variables that we zip, that we glue. The variables that we glue are now the weight 0 and weight 2 variables, and the weight 0 variables are not counted in the weight. So there is no, there's nothing to make it docile. There is nothing to make the powers of the weight 0 variables limited. So when you write all these differential equations, so and we wrote differential equations, nothing guarantees, or naively, nothing guarantees terminations of the sums. Okay? So what do? Well, okay, you treat the quadratic part, and really the quadratic part is itself a sum. So if you glue relative to only some of the variables and not all of them, then the quadratic part itself decomposes into a quadratic plus a linear plus a scalar. But anyway, you treat this part just the same as you did before. No docility was used there. And you are left with pairing something of the form e to the, or applying, or solving this differential equation, you end up solving, so I mean, for the last step, so after doing this, you still, so after using lemmas 1 and 2 as before, and they didn't require anything, you still need to solve, you need to solve what did we call it, the synthesis equation. And the synthesis equation was, what was it? Some d lambda of z lambda is equal to some 1/2 sum Fij di dj z lambda plus di z z lambda dj z lambda. And you solve it by iterations as before, and the issue is, does it converge? Does the summation terminate? And the point is that it does, because so the f is always of the form, so one of the variables is of weight 0, and the other variable is of weight 2. So, first of all, every time you apply the differential operator on the right-hand side, it lowers weight by 2. And so it's true that differentiation with respect to I, with respect to the weight 0 variables, doesn't terminate, so it's not nilpotent. You cannot, it's not the case that if you differentiate with respect to I finitely many times, you get 0, but it doesn't matter, because every weight 0 variable is paired with a weight 2 variables, and as a pair, when you apply this pair or this pair, it does stop. At some point, you reduce the weight to 0. So everything works. Okay. So everything works. And in fact, it's again nearly the same programs. I don't think I will have the time to show you the implementation, but basically, the same programs work. The sort of, the programs. Well, the summation stops at the same place. There is the exact same programs work, and the only difference is in superficial things. So the data structure, instead of just being triples omega q and p, you should be working with quadruples omega l q and p, and then when you're zipping the 1 variables, you partition these quadruples in one way, and when you're zipping the 0, 2 variables, you partition them in another way. But otherwise, it's exactly the same program. There is just really nothing, no real difference, except one. Sorry, so there is one difference, and this is the following. So the conclusion from all of this is that if you make a category DPG2, then DPG2 is computable. So it's kind of easy to compute things in DPG2, okay? Things in DPG2 have finite presentations. At least, sorry, if you crop the power series at some fixed power of epsilon. So they have finite presentations. In fact, since the degrees are all bounded, these are presentations of finite rank, of finite dimension, but over the scalars. So instead of being over Q, it's computable over the scalar. So part of the computation is happening over Q. This is happening over Q. But part of the computation is happening over the scalars. And what are the scalars? The scalars so far are power series in the weight 0 variables. So there are power series in the alphas and the b's. But the ring of power series is itself not computable. Right? I mean, what is a power series? A power series is an infinite list of elements, of coefficients. Or, I mean, a priori, I don't know how to implement power series. I know how to implement cropped power series, but not full power series. So this is bad news. So we want to remove it. But you see, we don't need the full ring of power series. All we need is some subring of the ring of the power series that will be closed under all the operations that we need to do and will contain our initial conditions. Our initial conditions include exponentials in the variables, in the weight zero variables, and the weight zero variables themselves, like here. And this will persist. So, I mean, I'll have to, when I'll make the same theorem about QU, I will have to tell you that for QU, it's the same. Okay? So we must have exponentials and the variables. Now, the gluing operations of the 1, 1 variables just treat the coefficients as a ring. So I just have to make sure that I close, as a ring, but it also includes computing determinants and inverting matrices. So I need to be able to invert. So my ring of coefficients must include the weight zero variables, their exponentials, and then any rational function on these. So instead of this, I will replace it by the ring of rational functions in alpha I, e to the alpha I, beta I, and e to the beta I. And this is, of course, a subring of this, because every rational function you can expand as a power series. And there is still one problem. And the one problem is that I also need to be closed under the last operation, and the last operation is differentiation. Right? Because I sometimes differentiate. Only finitely many times, though. But you see, fortunately, if you differentiate a rational function in these variables with respect to any of these variables, you still get, so rational functions are closed under differentiations. The derivative of a rational function in the variables and their exponentials is again a rational function in the variables and their exponentials. So this is good enough. And now everything is genuinely computable. Okay? So again, it's this thing where things look hyper complicated and they are delicate, but the program to implement them are in fact already written. So, like when you tell Mathematica to differentiate a function, it just doesn't care what it is. So it will differentiate, and it will produce an output. So it will differentiate these functions just as well as it differentiates anything else. And the programs are essentially already written. All you have to do is to feed them with the correct, with the elements written in the right order. Okay? So oddly, from a computational perspective, it's actually very simple. Okay. The challenge, of course, will be to show that not only everything is computable for CU, but also for QU. And I'll have to mention QU next week. Okay, I want to stop with that. So and go back to the proof that this was the correct formula. And I remind you that what we found is that, well, or what we needed to prove, that some product of exponentials was equal to some other product of exponentials in CU. And what we found is that applying a representation, a two-dimensional representation rho, this is true. And the two-dimensional row representation rho was faithful, so injective. So rho is injective on the Lie algebra. So CU was the universal enveloping algebra of some Lie algebra, and rho was injective on the Lie algebra. So everything looks good, except we need to know that it's also injective on things like this. Okay? And this is surprisingly hard, because we need to understand exponentials in a universal enveloping algebra. Or more precisely, in a universal enveloping algebra completed, so with some coefficients, small coefficients allowed, namely the Greek letters. Okay? So I started working on that, and here's where we were. So we in a general coalgebra, so a universal enveloping algebra is a coalgebra, and in a general coalgebra, co-commutative, sorry, I should have said here, co-commutative, in a general co-commutative algebra, we define two classes, sorry, co-commutative coalgebra, we define two classes of elements. One is the primitive elements. These are the elements that satisfy, so x such that the coproduct of x is x tensor 1 plus 1 tensor x. And the so-called group-like elements, which satisfy that the coproduct of uppercase x is x tensor x. And our goal, my goal, is to study primitive and group-like elements in universal enveloping algebras. And the conclusion will be that they are the same, that basically these correspond to the Lie algebra and these correspond to the corresponding Lie group, and every element here is the exponential of an element here. These are closed under exponentiation, these are closed under taking brackets, and if a representation is injective on these, then it's also injective on these. So the goal is to understand all of these in our context. We're not going to get there. Everything is taking longer than I'm expecting. But let me tell you at least two things. So the primitive elements so claim 1, proposition 1, primitive elements make a the definition made sense in a coalgebra, but the theorem is for Hopf algebras. So in a Hopf algebra, so for the definition I never needed to use the multiplication operation, only the co-multiplication. But for the proposition, I need the co-multiplication. I need the multiplication as well. So primitive elements make a Lie algebra under the commutators. So in other words, what I'm asserting is that if x and y are primitive, then the bracket of x and y, which is xy minus yx, the commutator, so here is where I need a product, is also primitive, is also. And in fact, I don't need this theorem for what follows, but for completeness, like I cannot go through primitives and group likes without saying this. So proof, well, the proof is kind of silly, I just compute. So the coproduct of xy minus yx is, wait, I think we did it, no, we did it in a special case, but this is equally true in the general case. So the coproduct of xy minus yx is, which is, let's be full. The coproduct of the bracket is the coproduct of xy minus yx. Yeah, we've done it. So this is, so first of all, the coproduct of xy is the coproduct of x times the coproduct of y. That's the Hopf property. So this is x tensor y plus 1 tensor, x tensor 1 plus 1 tensor x times the coproduct of y, which is y tensor 1 plus 1 tensor y, minus the same thing in the opposite order, so y tensor 1 plus 1 tensor y times x tensor 1 plus 1 tensor x. I think I'm only writing this to remind you that we've written it already in a different context, but it's still true. But this came out to be the bracket of, so xy tensor 1 plus 1 tensor xy. And this is exactly the definition of primitivity. And then, well, I mean, this shows that it's closed under brackets. You still need to show that it satisfies the Jacobi identity. But this is automatic for commutators. And you also have to show that it's anti-symmetric, wasting your time. Here's the more interesting proposition. So proposition 2, group likes make a group. So I need to show two things. I need to show that the product of two group-like elements is group-like, and that every group-like element has an inverse. So the product, so suppose x and y are group-like, let's compute the coproduct of x bracket y. That's the coproduct of x is x tensor x. The coproduct of y is y tensor y. The rule of multiplication this is all happening in the algebra tensor itself. So the rule of multiplication is you multiply the first factor with the first and the second with the second. So this is xy. This is xy tensor xy QED. Okay? And I will not show why every element has an inverse because I ran out of time, but check, homework, the antipode of x is its inverse, if x is group-like. I hope this is true. Thank you, Jesse. Oh, here I should have said not in a Hopf algebra, in a co-commutative. We still need a co-commutativity. Okay. Yeah, I'll quit, and I still owe you the rest of the proof. It's taking a lot of time because I'm digressing. Okay, so see you on Monday.